Swayam Prabha. Digital India. Educated India.
Today I'm going to be talking about the containers and Kubernetes era. Yesterday in both the sessions, you heard Suparna and Mohan talk about how the operating system evolved and how the virtualization technology developed and how the nuts and bolts of virtualization on an x86 and Intel's and AMD's platforms work. What are the challenges and how the system does whatever it does so seamlessly. And I think during yesterday's session, Mohan briefly touched upon one of the aspects of virtualization that is called secure resource partition by HP, and Solaris called it zones, and Berkeley Unix called it jails. So you had the different terminologies, and the latest terminology that is being used to describe that is called containers. And this is, although the idea behind itself is old, as you will see in the coming slides, I will talk a little bit about history of it, of where it came from. You will learn a good deal about what this is about. And so let's, without further ado, let's get started on that. So what are we going to talk about today is, I'm going to talk about what a container is and how it is not, how this is built using the building blocks from operating system technologies that that were developed since 2000s, in the beginning of 2000s. And you can see that although containers is the hot new topic now, the roots of it are quite old. And that way you can possibly relate to what Suparna was mentioning yesterday, that ideas were ahead of their time a little bit. So the major technologies for namespaces and C groups. And then we're going to learn about what are the challenges when it comes to containerization in networking and storage areas. Basically, getting the required storage into a container wherever it runs, how that is a challenge and how it is overcome, and how sharing a system resources among containers poses challenge and what the solution is. And then we're going to talk about something new that has come up that's called the orchestration. So you might have heard of this buzzword called Kubernetes. So Kubernetes is essentially an orchestrator. We're going to learn about what orchestrator means and what a profound impact it has had on the way the applications are developed, written, and deployed today, as opposed to how they were done just a few years ago. And although the idea itself is not old, the ecosystem required to realize that idea has just opened up a lot of possibilities. And you're going to learn about that, how it enables the portability. And we're going to learn a little bit about what is meant by declarative specification. And I'm going to touch upon a little bit of what is meant by monolithic application versus a microservice based application. You will hear about many of these things in your your general technological education that you've been having. People call that lambda computing. Some people call it serverless computing. Some people call it microservice. We're going to talk about all that. And later on, we're going to have a hands-on lab where I will walk you through some of these uh, technologies hands-on on an Ubuntu system. And you will be able to appreciate it well when you actually see it in action, and as we dissect and do some analysis of how the system has done what it is showing outside. So you'll be able to better appreciate that. So some of the prerequisites for this is, the first is the format of this class will be little bit of theory, and even in the middle of this next 1 hour, we'll take a pause for about 5-6 minutes for you to get onto a system and see it in action. So I am assuming that you have been told that you're given access to an Ubuntu system with some software installed on it. I hope that is the case. So may I have a show of hands? I mean, in the virtual room itself, you have on the top right corner, right next to participants, you have a icon where you can raise your hand, which says you can communicate like that. And can I see a raise of hands if you have access to an Ubuntu system right now that is booted up? Okay, I see Adi has raised his hand. It's very good. Mayank. Good. Dinesh. Good. Okay, I see 3 hands up. How about the others? Do you have access to the system, or are you still booting up? I can wait for a few minutes if you are still booting up your Ubuntu system. Okay, so what I am seeing is that not everyone has had their Ubuntu system booted up and ready to go. So what I suggest, or I strongly suggest, is you get access to the system right away and try and boot up the system and keep your Ubuntu terminal ready. So that way, in the middle of this class, after covering a little bit of theory, when we switch to the system, you will be able to do some hands-on and see what I'm talking about. So that way you will be able to learn online. Of course, later on in the hands-on lab, we'll go a bit more serious and try and actually deploy some containers, orchestrate some containers, and learn all about it and see the system in action. So I will not wait for this. I will continue, but I strongly suggest all of you, whoever has not have booted the Ubuntu system, get access to it now during the class. Try and boot it up and log into it, and hopefully by the time we get to the first hands-on session, you will have your system ready. Okay, so the platform that we are going to use for this is called Minikube. It starts up a one node Kubernetes cluster. Do not worry about what this says and what it does. As this class progresses, you will be able to see it much more clearly. And when once this is done, you're all set for doing the hands-on sessions. And the same Ubuntu system will be using for the afternoon hands-on lab, and hopefully it'll be fun. Okay, so let's start about what a container is. So to briefly describe it, give it a textbook definition or sort of a very logical definition, I can say container is a program that runs in an isolated space. So program experience will be as if it is the only program running on the systems, but many such programs run simultaneously on the same system in the same operating system instance. And there's a magical new component called container runtime that makes this happen. So on the right hand side, you will see the picture. At the bottom of the picture, you have the bare metal servers. And of course, you can run any operating system on the bare metal servers itself. For example, the Ubuntu system that you have right now, it can just run on a bare metal server. But the most common one that you see today is that on the bare metal servers, you have a hypervisor. I mean, you all are aware of what hypervisor is from yesterday's session. And this hypervisor can host one or more virtual machines. And each of these virtual machines can have their own operating system. For example, on the left-hand side, you will see a green box bare metal, a blue hypervisor on it, and there are two red-colored virtual machines, and there are two OSs. One virtual machine can be running Windows, the other one can be running Linux, and so on. There can be any number of virtual machines like that. And ideally, you would see, as Mohan explained yesterday, once you have a virtual machine going, these operating systems are isolated from each other. And anything that happens in the operating system is contained to that virtual machine, and it doesn't really affect what is happening on the other virtual machines. And now we will take it a bit to the next level, where every operating system can run a user space program called a container runtime. Uh, Remember this word, the user space. This has nothing to do with any of the kernel. That means we do not change the Linux kernel, or we do not change any operating system. Just there's a user space program called a container runtime. And this container runtime can run up multiple applications and keep a tab on them, and provide them an isolated space and restrict what they see. So this is the keyword, that is restrict, which is each container, although it is sharing the same operating system resources and running on the same virtual machine, or probably on the bare metal directly, it will only see what it is allowed to see by the container runtime. That means if the container runtime says that one application is allowed to allowed to use only one CPU, the application sees only one CPU. And if it says the container runtime says this container is allowed to use only say 1 GB of RAM, the application will not be able to use more than that. If the container runtime says this application will be allowed only to use device number 1 and device number 2 and nothing else on this system, that will be done. And we are going to explore about what is the magic that makes all this happen. So once this is implemented, what you will see is an isolated space that is provided to each of these applications, where they think they are the only program running on the system, whereas there are multiple such container instances. The advantage here is that each one of them will think they own the system, and they have a complete experience of an operating system, but they are only seeing the limited set of resources uh, that the container runtime allows it to see. We'll see how that happens in the coming slides. So let's see how this magic happens. So there are some building blocks in the Linux kernel that makes this happen. So the aim of these building blocks is, as we said, we want to provide an isolated run environment for programs inside a single OS instance. That means I put up a Ubuntu Linux, I must be able to run any number of containers on it, any number of programs on it. Each program thinks that it has the exclusivity, is the only program running on the system. So in a very loose sense, you can say that this is doing the job of the hypervisor. Instead of providing separate machines, it is just providing an isolated environment where the applications can run. So potentially you could just remove the VM that you see on the right hand side here and the hypervisor here and get the exact same experience. But in practicality, it's not so. We still need the hypervisor and the virtualization technologies because of the reasons that you are aware, which is you have a large number of bare metal servers and you need to have more than one point of isolation. The problem is if you have one instance of the operating system failing, it should affect only a limited set of programs and not the entire system. That means if one of these VMs fail, all the containers that are running inside that OS instance fail simultaneously because they are dependent on the operating system, and we don't want that to happen. We want to limit the fault. We want to have much uh, smaller fault domain. And programs still share the resources of the single OS instance. For example, if uh, there's so much of memory. The operating system has, let's say, 8 GB of memory, and it has allocated it equitably to all the containers. They still share the same operating system. All system calls go to the same operating system instance. They also share the fault domain, what we talked about. So there are two fundamental building blocks in the Linux kernel that make this kind of an isolation happen. The first one is called C groups. So this is a feature that has been in Linux kernel since 2007. So what it allows is it allows you to create an a new abstraction called a C group. And essentially it is a short form for control group. So on any Linux system, you can create a control group, give it a name, and you can set certain limits to this control group. For this control group, and saying, I will limit the amount of CPU or the amount of memory and many other resources. And then you can start adding whatever process you want to be part of this control group. So this control group now sets the outer limits. The kernel, there are changes that are done in the Linux kernel that takes care of enforcing those limits. So all the processes that belong to this control group are now bound by the rules set for that control group, for that particular C group. And this has been in Linux kernel since 2007. And this is the basic building block of isolation, that is limiting the resources. Now, the second part that we talked about is the visibility limits, which is I also mentioned that the container runtime decides what a particular program is allowed to see and not allowed to see. While the C group provides the limit on how much resources it is allowed to consume, the namespaces give the flexibility of controlling what it is allowed to see. And this is a feature that has been in Linux kernel since 2002. And what exactly is a namespace? So let's start by saying that every process that runs in a kernel on a Linux system belongs to a particular namespace. There's always a default namespace. A namespace is simply one ID and a number. So every process when it's created, in Linux, you always create a process with a clone system call, or you type an ls command. Essentially, what happens is that process is spawned and it is given a new PID and all that, along with all the resources that are given, all the identifiers that are placed to make this process unique. A new thing is added. It's called a namespace. So when creating a process, you can actually put it under a new namespace and then start placing restrictions on what that namespace entails. This is essentially the idea behind namespace. So once that is set, everything else falls into place. That is what it's allowed to see. So for example, how does this change what devices it's allowed to see and what devices it's not allowed to see? Going back to the basics, you will see that a program can only identify the devices by looking at the /dev directory. Fine. So if you can restrict what it can see under the /dev directory, then you've essentially achieved limiting the process to seeing what it wants to see. It cannot see anything more than what it's seeing there. Similarly, with the other processes, if you limit its access to the proc file system, it will only see its and its descendants processes and nothing else. We are going to look at all that in the coming hands-on sessions. So these are the two basic building blocks. There is also a third building block that has been around in Linux for a very long time, and that's called chroot. You must have heard of it. It's called chroot. You can just go to any Unix system and do a man of chroot and it will tell you what it is. Essentially, what the chroot does is it switches the root directory of a process to whichever directory you specify. So for example, if you boot up a Linux system and you log into the system and you go to the root directory, you will see the boot directory, you'll see the dev directory, you'll see proc, and you'll see the whole bunch of things that are the actual root file system of that system. However, for a particular program, if you do execute the chroot system call and give it a new directory, a new home, that becomes the root directory for that particular process. And no matter what happens after that, it will not be able to come back to the original root unless whoever executed the chroot executes again to switch it back to the old root. So now we have seen by starting a program and placing it in a new control group and setting certain limits, we have limited how much resources it can consume. By creating a new namespace for this process, we have restricted its visibility. And by using the chroot functionality, we have essentially um, switched the view of the program to a new root directory. So this is essentially what happens, but there are a lot more things that a container runtime does besides these, but these three are the fundamental ones that achieve isolation. So a C group is a set of resource controllers. So I talked about C groups. So control groups restrict how much resources is each program allowed to consume by placing them in a C group and setting certain limits. So the way the Linux kernel has been built is that one can keep on adding more and more controllers. Each resource controller is in charge of restricting one resource. For example, there is a resource controller for CPU, which follows the directions given in the C group settings, and it prevents the processes that belong to the C group uh, from consuming any more CPU than what is allowed for that C group. Now, this is called a CPU resource controller. Similarly, there is a memory resource controller and there is a device resource controller. There are many controllers. We'll see about that in our hands-on session. So C groups are hierarchical. This is a very important point. That is, you can create a C group inside a C group, and the overall limit applied to the outermost C group is followed or implemented in the hierarchical C groups. For example, you can have a bigger C group that has limits of 4 CPUs and another 2 C groups inside it which restrict to 2 CPUs each or 1 CPU each. Any of these, but the inner C groups cannot have anything more than what is allocated to their parents. This is the hierarchical one. Very useful to set larger limits and then divide it among the other C groups that are under it. So how are C groups managed? Do you just run some certain commands or how do you do that? Or is that new system calls to do it? No, it's actually quite simple. There is a new type of file system under the sys file system and a new file system called a C group. The type of the file system is the C group. And by simply doing a mkdirs inside the C group and directly doing some settings to that, you will be able to achieve that. We will do that in our hands-on lab to see how that is done. A namespace, again, is an identifier that is associated with every process, and it sets the visibility limits as we talked about. So when the process is started, you can either attach to an existing namespace or you can create a new namespace and set its own limits. And notice the behavior that this is not hierarchical. There's a single, the namespaces are in a flat hierarchy. You can go on creating namespaces and they are not hierarchical. And the default behavior, what happens if I create a process without setting the namespace? It simply takes the namespace from its parent. And if you are in the shell and if you started out without setting any new namespaces, you will be seeing the global namespace where there are no visibility limits. All processes can see everything that they're allowed to see by the file system permissions. Okay, now is the time for our first exercise. I hope everyone has their Ubuntu system. So let me also shift focus to my Ubuntu system here. And I have it here. And let's do this exercise. So let me see a show of hands once you have the terminal ready. All right. I see one hand went up. All right. 2, 3. All right, for those of you who don't have the terminal, you can probably just watch it as I type it in. But I really suggest that you get the terminal going because playing with these things will be a lot more fun and you know uh, it's more intuitive when you actually do the stuff by yourself. Okay, so let's do the first thing. Let's start the uh, Kubernetes cluster. So I'm going to do Quite simple. So essentially what Minikube is doing is it is starting a new virtual machine on the Ubuntu system, and it is going to start all the software packages that are needed on that VM pre-installed, and it will start that VM and it will control the VM to start all the necessary programs, start them up properly and set it up. Here it is starting it with Kubernetes version 1.20 and Docker 2010, as you can see on the screen. This will take just a minute or so. This is a one-time thing which is starting it, and there you go. So now there's a new Kubernetes cluster, a Docker host has been started, and let's do the next part. What does it say here? It says enter the virtual machine with Minikube SSH. All right, I'm going to do that. Let me start it from my second terminal. So here you are seeing that I have the terminal from where I started it. This is the Ubuntu generic. This is where I started it. And now I have SSH'd into the actual virtual machine. So if you see, I have actually, it appears that I have entered a different system altogether, but it's actually a virtual machine, a single instance of the virtual machine that has been started by Minikube. Now, this virtual machine has the container runtime installed, and let us look at how the control groups or the C groups look like in this system. So what do we say in this exercise? Let us look at the file /proc/C groups.
So sorry to interrupt,
Sure.
Prachi here. So how is
Yeah.
it like students can interrupt if they have any doubts directly to you or how?
Absolutely. Yeah, sorry to mention that. Yeah, anytime and if you have any doubts, you can always interrupt me, stop me, and say, "Well, I didn't get this part, or can you explain this a bit more?" Please feel free to interrupt me anytime. Thank you,
Because
Prachi.
I think Mayank is facing some problem with some setup. He wrote in the chat box. I insist, Mayank, you can directly ask. It will make these things faster.
Yes, sir.
Yes, please.
Excuse me, sir. Yeah, hi,
Yes.
sir. So I installed this Docker in my Ubuntu system using the in the first mail that was provided, like install the system, but Minikube is not working for me.
Or did you install Minikube? That is using the instructions.
So in the instruction, it was Docker, mph, and chemo. So I installed the Docker,
Mm, you do
but
not need to install Docker, Mayank. The instruction file, remember it right, was if you're looking at the slides, this is how this is all that you need to do. That is, you do not need to
okay.
install Docker at all. You have to install the virtual box. Uh, are you able to see the slide that I am sharing right now?
Yes, sir. Yes, sir.
Yeah,
Yes.
you need to install this, and this is all you need to do. You do not need to install Docker on Ubuntu at all, because the Docker that we are going to work on will be installed by Minikube in the virtual machine that it starts. You do
So
not need to do that.
do we need to have a virtual machine? Because I am working on Ubuntu itself.
Correct. So on Ubuntu itself, when you do this one apt install virtual box, it starts the virtual box as the hypervisor. It will start and the Minikube will create a virtual machine for you. You do not need to do anything other than what is given here.
Okay, sir. Okay, sir. Yes, sir.
Yeah, a Minikube is the only program that you will need. You do not need to worry about Docker, installing Docker, Kubernetes, or configuring them or any such thing. Everything will be done by this set of commands that are shown on the screen.
Okay, sir. Thank you, sir.
Sure. Yeah, I mean, probably you can get started with those commands by installing Minikube on it, and you do not need to do anything else like installing the Docker on it. So hopefully by the time we get to the next exercise, you will have the whole system set up. In the meanwhile, probably you can just look at the screen that I am sharing and see if, this is how it should.
Yes.
So here
Yes.
you have this is the virtual machine that has been created, and as you can see, as Mayank was just mentioning, this has Docker already installed on it, and it has or Kubernetes also installed on it. So let's just go to okay. So what are we actually seeing here? What we are seeing here is that the proc file system gives you generally information about the file systems. For example, if I say cat proc file systems, this tells you the kind of file systems that are installed on this Linux kernel and ready to be used. Similarly, if I do proxy groups, it is now showing me the resource controllers that are currently installed on this Linux kernel. CPU set, it restricts what set of CPUs a C control group is allowed to use. Then there is a control group called CPU and accounting of the CPU. Then there is a resource controller that determines how much of block IO is allowed, how much of memory, and what devices. And you will see many of such resource controllers that are present in this particular system. So this tells you the resource controllers that we talked about that will do the restrictive part of what a program, how much of resources a program is allowed to do. Now let us look at how many control groups are actually present in the system right now. So to do this, as I mentioned, the C group is available in a file system called /fs and C group. Let's go in there and see what we can find there. So here you will see there are, for each of these resource controllers that we saw, we see that there is a corresponding entry here. That means we have CPU set and then there's a CPU set. Let's do a little bit of snooping around and see what we see inside CPU. What do we see here? So here you see uh, plenty of files, and most importantly, you will see there are two specific directories that you see. That means if I do this, you will see system slice and user slice. These are the two C groups. Suppose that if I want to create a new C group, which restricts the amount of CPUs, what exactly do I do? What I do is I will just create a C group here. Okay. Boom. So I created a new C group here with my name in it. And let's see what's inside the C groups. Automatically, it has created some of these files, and each of these files have signify something. These are some of the settings that can be done on the C group that I just created by the name Raman. The most important one that you see here is a file called tasks. Let's see what that file has. This file is the one that says which processes belong to this particular C group. Now, currently this shows that there are no processes that are part of this control group, but there are. Let's look at another C group that's already created. you will see a similar structure here. But if you see the even here, it doesn't have anything started yet because we haven't started any of the services. But this is how the there you go. So in the main control group, in the CPU group, you will see a lot of processes have been placed. A lot of PIDs have been placed. Each one of these will have the restrictions that are applicable to this particular, for any particular C group for which it belongs. So let's do a little bit of experiment on what the namespace is about. So here we say, let's look at /proc/self ns. So self is a special entry that's created in the proc file system that refers to the currently executing program that you are part of. That is, whatever you are executing. In this case, it will be the shell program. So let's go to self. And if you look at this is the program I'm currently running, it says it's bash. That's understandable. And let's go to ns. There you see that it says that the currently executing program belongs to one particular C group, and the inter-process communications are restricted to a namespace called 4026531.839 and many other mount points, the networking and the PIDs, and each of these things they are associated with a namespace ID. So when the program starts, it can be placed in any of the existing namespaces. Looks like this program has been placed in one of the existing namespaces, and this is the namespace to which it belongs. I hope that was useful. Was everyone able to look at that and follow that? Can I have a show of hands that you were able to relate to what was done earlier? Does it make sense? Were you able to relate to what you heard earlier about C groups and what you saw in the system with C groups and namespaces? Can I have a show of hands? Okay, one. Uh, okay, so it looks like you were unable to relate to what was presented earlier to what you saw just now. So can any one of you speak up which is the part that you found difficult that you're unable to relate to? I'll try and clarify that. Anyone?
Yeah, hi. I'm trying to do this, but it's stuck with downloading. I just installed this Minikube, so yeah, it's taking a bit of time.
Yeah, the upgrade path takes a bit of a time, and yeah, hopefully it will get over soon, depending on network bandwidth, I think.
Yeah.
How about others? Do you guys have any other questions?
Yes, sir. I also just installed it and it's still not working. Like exiting due to PRV box device missing. It's showing this error. I don't know. Failed to start the host and
Yeah.
I installed the Minikube and just like you said, and still it is not working. I'm still figuring.
Okay. Yeah, probably let us not waste time trying to debug that. Probably during the break, you can have a look at that, say,
Yes,
what
sir.
how
Yes,
this
sir.
is, and try and get that. Then let's move on and see where what's the next thing that we can learn. So as we learned, containers are built on top of the C groups and namespaces infrastructure. The basic nature of a container is ephemeral, which means that the container is not expected, or the basic nature of a container is that it is invoked to perform a particular function. It does the function and then it is dismantled. So it is not a permanent thing that is started and it is kept running. That is the basic nature with which containers uh, are created. So how exactly is a container created? We take a program and identify all its dependencies and create a directory hierarchy. And then since we built the program, we know what resource limits and visibility limits it is happy with, and codify them into the program itself when we create the what we call as a container image. And once this is done, what we do is we prepare the necessary and C group and namespace information necessary on the system. We take the packaged directory that we built earlier with all its dependencies, and we put them in a temporary directory, start the program in the new directory and make it the root directory for the new program. And we apply all the C group and namespace configuration with all the resource limits and visibility limits. Once this is done, the new unit now is a fully independent container. And if the program starts up and if it looks around, it sees it is the only program running on the system, and it only sees what it is allowed to see, and it's only be allowed to consume as many resources as it is allowed to. And the important thing here is all the dependencies such as the libraries that it uses or any of the other programs that it uses will be specific only to this container. For example, there could be one container that is running a compiler of version 4, whereas there could be another container that has started which is using a compiler version 6, if assuming that both are some built environments. Similarly, it applies for other libraries too. So what happens when the program exits? When the program exits, all the C group and namespace and temporary directory that was created for it are deleted, and the system goes back to what it was before the container was started. And when the container is started again, the entire process repeats. So this is the program experience will be the same since nothing changes from its viewpoint. Every time the container wants, certain things are set up for it. It is made to run, and when it exits, the whole thing ends. Now, what the important takeaway from this particular slide is that since it is ephemeral in nature, and since everything that the program needs is already packaged and available in a portable form, it can be put in some kind of a repository, and you can take this program and run anywhere. For example, it could be running on system 1, and after it has done its job, after a while, if you need to run it again, you can run the same program without having to do any special configuration on a different system. So this is essentially one of the advantages of containers, which is the portability that it gives. You build a container once, you'll be able to run it anywhere as long as there is a container runtime on that particular system. So how is this implemented in real life? So there are two portions of it which you need to visualize. One is the development part. How do we build a container? We talked about identifying all the dependencies, packaging them into a particular directory, and then creating a container image out of it, and then actually running it where you can run it on any system. So these two parts, let us call them dev and ops, meaning development, ops standing for operations. Operations is where we deploy and start and stop the container. Dev is where we actually build and publish the built program. So there are dev tools that are used to create and package a container image. Docker is a command that helps us do that. And then there is an image repository. That means once we build a container image, a program with all its dependencies, we push it to a repository. It could be a private or a public repository. Docker hosts a public repository where anybody can push any image they want. And similarly, Also, is also on the popular repository on the internet. Plus, some people are very worried about, okay, I don't want to publish my program on public spaces. You can host a private repository using the software, same software that Docker public repository uses. And the operations. So how does the operations work? Once something is available in a repository, there are certain tools available to push the container image from a repo. That means there are commands like CTR, which is part of the container D host. And then there is a Docker command itself. You can pull an image from a repository and you can run them. And for we talked about when the container is run, we take the package downloaded and we create that package. We set up the root directory exactly as the container program expects to see. And then we hand over the control to the program with all the limits that we have specified. So the container home directories are constructed on the local storage. And the important thing, the most important role is performed by what we call as a container runtime. This is the program that takes these images from the repository, deconstructs them, understands the limits that they need, understands the limits and the visibility limits that have to be applied to it, and applies to them, creates a separate directory from the manifest given, and it hands over the control to the program specified. And then the container runs in their own spaces. This is illustrated in the diagram that you see on the right side. You have an image repository. The development people that you see, the dev tools, they will build the image and then they will push it to the image repo. And from the image repo, the operations, when you want to deploy it, you pull it from the image repo and then you feed it to the container runtime. And the container runtime takes the image, deconstructs it into the local storage, and it instantiates the containers. Here you see two containers running A and B, which have been instantiated from an image that has been pulled from the image repo. And it all runs on the Linux kernel, which has C groups and namespaces installed on it. Is this clear, or this is an important slide to get the basics right? I hope this makes sense. And we'll build more on this slide about what other things that that are added to it to make to solve some of the challenges. So to put it another way, this is what we talked about. Yes, please.
Sorry to interrupt. I didn't get the difference between op tools and dev tools.
Okay. So we will talk about this in this slide in a bit more detail, the current slide. So the dev tools are the tools that you use, that a developer uses to take a program. I mean, you might write a program in either say Go language, C++, C, Python, whatever language, and then you written a program. Now you want to convert that program into a container runtime and push it to an image repository. So the tools that you use to contain the normal programs that you use for building the program is your the language compiler and link it to the libraries and everything, right? These are the normal dev tools that you use. But once you have built the program, to package it into a container form factor and then push it to an image repository, you use certain tools. Those tools are called dev tools. So in this case, Docker is the most popular dev tool. It happens to be both a dev tool as well as an operations tool. So the operations tool, the ops tools are the ones that are used to pull the image, the container image that has been uploaded by the developers into a system, deconstruct it and deploy it as a container. So in this slide, what you're seeing is two cycles. The one on the left is the developer cycle. The one on the right side is the operation cycle, and they are both connected at the hip. The way it happens is the developers builds a program, and then he creates a container image for that program, and he pushes it to the image repo. And the operations people will now be waiting for the new image to show up. Once it is shown, once it shows up, they pull the image from the repo and stop the existing container, and they'll restart the container with the newly obtained image, and they will monitor and collect the logs and give the feedback to the developers, and the developers will be waiting for the feedback. And based on what they see, if they want to change the program, they change or enhance the program, build the program, recreate another image, push it to the image repo, and then it gets deployed again. So this is the dev and the ops cycle. Does that answer your question?
Yes, thank you.
Sure. So this is what you normally call as the DevOps cycle. Obviously, this is a very, very simplified version of it. Nobody writes a program and directly pushes it onto the production. There are various staging areas in between before whatever you developed is actually deployed on the production servers. There will be a staging areas, there will be testing cycles and plenty of cycles. But this is a very simplified view of how things happen in a DevOps cycle. And in the container world, there are automated tools that do this every day. For example, if you are using any of the cloud services like Amazon or others, you can keep working on your program, and when you have something to update, you just push it to the repo, and the rest of the things will be done by automated tools. They will take your new program, and they will decommission the current program that's running, replace it with a new version of the program, and immediately it goes live on your website. So this is like an entirely automated process of how things happen, but it goes through various stages of validation, verification, and all that. But essentially, dev and ops cycle is how things happen in the container world. Okay, so let us see. Let's take a little bit of pause here and look at exactly how this happens. So let's start looking at the container runtime that we talked about. So the container runtime that we are using in Minikube is Docker. So let's look at what Docker is up to on my system. I've already started Minikube, and I am into Minikube SSH, and I'm into the virtual machine. So let me look at this is the container runtime that I'm running, and there's a client part and there's the server part. So let's look at very interesting. You will see some of the have a look at this particular window. Let me make that a bit bigger in case you want to look at it. So this is how it's looking. So the Docker is running its application container engine, and can you see that it has created a new C group under system slice called docker.service, and it's running quite a few containers. So there are under system.slice, it has this many processes. The numbers that you see on the left side are the processes, and what is the command line that has been used to start the container. So in this case, the program that is running is dockerd. It has been started with this many options, and you have a process PID 3576, which is actually a container of it's started a container. How I know it's a container? Because it's using containerd, and it's the container ID that has been started is this. And here you will see some of the logs. That's probably not useful for you, but anyway, this shows you how the C groups and the container runtime interact together. Let's see what do we do next? We did the Docker version. Now let's look at on this particular system that we have, what images are available. We talked about container images being pushed by the dev, and on the system where we are expected to deploy the containers, we should see some images. Have you pulled any images on this system? Let's look at that. Okay, very interesting. It looks like on this system, we have quite a few images. So there is there are 1, 2, 3, 4, 5, 6, 7, 8. So there are 10 images available, and each one of them have been created. You have when it was created, and you have the tag, and you have the unique ID for the image. Great. Now let's see if we can download a new image of our own, right? I think I'm sorry for this time. How do we pull an image from the repository? This is the op version of what I talked about earlier. Let me run a simple program called pull. Right, downloaded the image. Let's do the same thing again, what we did earlier. Can you see that we have been able to successfully download this image that was built 3 months ago, and we just downloaded it. Now, how do we run this as a container? So what we do is we do docker run and run the word. Exactly. So this is a very important output that you are seeing. So what exactly happened here is explained in steps 1, 2, 3, 4, and 1, 2, 3, and 4. Have a look at that. So it says Docker took the following steps. The Docker client contacted the Docker daemon. The Docker daemon pulled the hello world image from the Docker hub, or it was already present in it. So it skipped this step, created a new container from that image, which runs the executable, produces the output that you are currently reading. So I'm sure you found this useful. This explains a series of steps that happened that we talked about how the C groups and namespaces work together and how the image is pulled from the repository, instantiated, and started. Now let's look at what containers are already available. Docker ps is the command that will tell us what containers are currently available. Oh, this is a pretty big list. It shows that many of these are the currently active containers on the system. And you will see plenty of information. Most of these are processes that have been started for Kubernetes. Don't worry about them. But if you had the hello world still running, you would see that listed here. But you will see that a container has already been created when we ran it. But sorry, was there a question? Okay. So here you are seeing that it says that it's exited about a minute ago, but if that program was still running, it would show up in the earlier list. But here you're seeing that that container is created, but it is no longer running. This container can now be restarted without having to pull the image or without having to reconstruct it again. I hope you are able to relate this to what we just talked about how the containers are created, pushed to the repo, pulled from the repo, and deployed on a system. So I think it's we can proceed to the next part. Is we're going to talk about networking and storage challenges and how they are overcome, and we're going to do a couple of exercises of how those are realized on a Ubuntu system with the Minikube and Docker.